Hello and welcome to my presentation on the fluid mechanics of social distancing. Today I'm going to be presenting my project and how I've been preparing for it. So what am I going to go through today? Well, first of all, I'll give a quick overview of the project. I'll then explain the context in which it exists and the motivations for it to take place. I'll then give you some detail on the aims of the project and the objectives which I'll use to achieve it. And then I'll finish off by showing you some of my simulations. So what is my project? Well, first and foremost, I'm going to be looking at human sprays, so things like coughs and sneezes. And I'm going to be looking at how to model the dispersal of these sprays using CFD. That is, how far they travel, at what height, and in which directions. There are various approaches which can be taken when modeling these sprays in CFD, and I want to find out which of these gives the most representative solution of a real human spray, and whether simpler, more computationally less expensive methods will still give good results. So that's the first aspect of this project. The second aspect of this project is to assess the sensitivity of dispersal to different environmental conditions, such as temperature and humidity, but also to different spray conditions, such as different inlet velocities consistent with coughing versus sneezing. So naturally, the context of my project on human sprays is COVID-19. There are various transmission mechanisms for this virus. There's contact-based transmission, there's fomite-based transmission, and there's airborne transmission. So contact transmission is where you come directly into contact with someone who has the virus. Fomite transmission is where you contact a surface which has become contaminated with the virus. And airborne transmission is when you come into contact with virus-laden droplets suspended in the air which infect you directly. It's important to note that all of these main transmission mechanisms originate with droplets that come from the throat, mouth, or nose. So all methods by which COVID-19 can transmit are dependent on the dispersal of these droplets. So if all droplets originate in the mouth, how do some of them cause airborne transmission and how do some of them create contact transmission? Well, it's all to do with the size of the droplets. Larger droplets naturally fall to the ground more quickly because of their larger inertia, and they splash down, creating a fomite. Smaller particles, on the other hand, are too small for this approach and become dominated by viscous forces, which becomes a phenomenon called Stokes flow. You can see by this graph here that as droplets get smaller, progressing from a diameter of 1 mm to 0 mm, the time to fall 2 meters tends to infinity. For scale, a particle of a micron size would take up to a day to fall to the ground. These lightweight particles are particularly important because they can remain suspended in the air for hours at a time. This makes them extremely susceptible to turbulence, which can carry them long distances. However, reference 1 shows that most of these viruses actually have a very low transmission risk when airborne, and this is mostly due to the viability of the virus, that is, how long it remains alive for. However, evaporation also has a strong effect due to their small size. This is very strongly affected by temperature and humidity. This graph from reference 2 shows the lifetime of the droplets, which is how long they can survive in the air before they evaporate. You can see that there is a strong function of temperature, which are these pairs of lines, and of diameter, which is each set of lines. You can see that humidity plays a strong role, as this is a logarithmic scale on the left. But also temperature has a reverse effect, with shorter lifetimes at small relative humidities and longer lifetimes at high relative humidities. Another very important factor is the breakup of particles. This is actually quite a complicated process and remains something that's very difficult to model in CFD, and so it will be beyond the scope of this project. So I'll just say a little bit about how these sprays are modeled in CFD. The first thing to say is that this is a multi-phase problem. The droplets represent discrete particles which are affected by a continuous gaseous air phase that surrounds them. When modelling multi-phase simulations, there are three main approaches. There's the volume of fluids model, shown here on the left. Each different phase, shown roughly as a different colour, is segregated from the others by a boundary, not allowing particle-level mixing of the fluids. This is typical in, say, an oil flow pipe, but can also be used for single droplets, though the extra complexity of modelling an interface equation means that this can be very computationally ineffective for sprays with many droplets. The Eulerian model is more similar to traditional CFD approaches, where the domain is discretized into a mesh, and each cell is allowed to contain a volume fraction of each phase. This gives much less resolution of the flow, as you can see here, but is far more computationally efficient than the VOF model. The third and final model, which gives the best resolution of small-scale particles, is the Eulerian-Lagrangian model. This uses an Eulerian approach for the continuous phase, but couples it with a Lagrangian approach for the discrete phase. Discrete droplets are modelled as spheres within the continuous Eulerian phase, and each particle experiences forces from this continuous phase via a coupling solver. This coupling solver can be either one-way, two-way, or sometimes four-way. The two-way solver allows both phases to impact each other, so that the droplets influence the air and the air influences the droplets, but it is computationally much simpler if the continuous phase is solved without the influence of the droplets, and then the droplets are tracked through that continuous phase, which is known as one-way coupling. However, two-way coupling may be necessary in particularly dense or heavy sprays where the particles do have a strong influence on the air. So let me just tell you a bit about what I want to achieve with this project. First of all, I want to bring further understanding to the fluid mechanics behind infection. So I'm going to be investigating the effects played by dispersion and evaporation in infection rather than the other factors in virus infection such as viability of the virus and survival rate. I'll only be looking at the dispersal of these droplets rather than considering how infectious a virus may be. The second aim of this project is to reduce dependency on empiricism in existing research. So much of the existing research into the infection rate of COVID-19 depends on studies from hospitals and schools that try and correlate existing environmental conditions with change in infection rate. However, this is very difficult due to daily changes in the weather, testing rates, and human immune response, so it becomes very difficult to see what any real trends are. This is borne out by the fact that most empirical studies give very different results. For example, I have 4 studies here with conflicting results. Gupta in 2020 noticed no change in the infection rate with humidity, whereas Liu et al. Found a positive correlation. Similarly, Tosepu found a negative correlation between temperature and infection, whereas Ma et al. Found a positive correlation. It's very difficult to determine which of these is fact and fiction, so adding to the breadth of knowledge that already exists would be very beneficial to the field. The third aspect of this project is to determine what conclusions can be drawn about social distancing from dispersal alone. So it may come out of the research that under indoor conditions there is no possibility for droplets to travel, say, more than a metre. In these cases you'd be able to say that the transmission risk is actually very low. In these cases you'd be able to say that regardless of lifetime and viability of the virus, or minimum viral load for example, there is very unlikely to be any infection because droplets simply cannot travel more than, say, a social distance. It may of course be that this is not possible to say, but this is an important study for the project. So how do I hope to achieve this? Well, my first set of objectives will involve running a set of sensitivity studies on the different ways to model sprays. I'll be looking at different turbulence models which are important to the movement of small droplets. I'll be looking at different coupling methods and how much coupling is required to achieve a representative solution. I also want to look at the minimum number of particles required for a representative solution, and whether different particle size distributions need to be used, or whether I can just use a single diameter. Once I have the outcome of these sensitivity studies, I'll progress on to the spray dispersal studies. So once I have the outcome of the studies on what the best way to model human sprays is with CFD, I can then go and put that into practice with these spray dispersal studies. So these will be looking at things like what the impact of sneezing versus coughing is on the dispersal of a spray. They'll also be looking at the things like the wind speed and the direction of the wind and how much that has an effect on the dispersal of droplets. The third and final aspect will be to look at how temperature and humidity affect dispersal. This is one of the more hotly debated topics in the literature, so it would be good to get some additional results for this, although it will have to include simulating evaporation, which is somewhat more challenging. So this is my timeline for the project. What I've just described are phases 2 and 3. There is also some preparatory phases, such as the familiarization phase, which is semester 1, and also phase 1, which is datum definition and preparation, where I'll work out what kind of test ranges I need to make. There are also some extension studies included, which may be completed if there is sufficient time. So let me tell you a bit about what I've been getting up to get ready for this project. Well, first of all, I've been looking at the data I need to model a typical cough or sneeze, such as the velocities and particle distributions and diameters and volumes. I've also been looking at the dispersal angles of spray from the human mouth. Secondly, I've been familiarizing myself with the multi-phase models in the StarCCM Plus CFD package. Most recently, I've put these simulations into practice and run an initial study on how particle size affects dispersion. To do this, I've generated this mesh. It's a rectangular mesh generated using the trim cell mesher with volume extrudes on the inlet and outlet, that is, the left and the right, to improve stability. This was primarily chosen over the This was primarily chosen over the polyhedral measure due to the uniformity of the cells, which match the uniformity of the flow. You can see on the floor of the simulation there are prism layers which are used to capture the boundary layer, which may affect the fall of small droplets. If I zoom into the mesh, you can see that there is a large amount of resolution around the subject and the region where the spray will land. This resolution in the mesh only affects the continuous Eulerian phase, as the Lagrangian particles can move at any point through the mesh. The effect of the mesh is therefore to resolve turbulence, which can be significant in a typical outdoor environment. So here are the results of the simulation. Each of these represents a different particle diameter, so there is 40 microns, 80 microns, and 200 microns. You see that the primary force acting on the small particles is drag rather than gravity, and so it has equal forward and downwards velocity. However, you can see that as the particles get larger, the effect of gravity increases on the particles, causing them to fall faster. As you can see, when particles get very large, they have such momentum when they leave the mouth that they travel a large distance before drag is able to slow them down, and then fall the most rapidly of all. So these are the exact same results as we would be expecting for this kind of simulation. But what about if you were to consider multiple particles at once? The typical way to model a droplet distribution after primary and secondary breakup has occurred is to use a Rosen-Ramler distribution, which is an exponentially defined bell curve. You can see here the results of that simulation. I've used a mean diameter of 80 microns with an exponential parameter of 2, which governs how steep the curve is, how concentrated the particle diameters are. This is typical in the literature. So you can see here that the results of such a simulation essentially represent a superposition of the previous three simulations. However, there aren't quite enough particles to give a fully representative solution here, as it is only a preliminary simulation. So I've been running a Lagrangian multi-phase simulation with an ideal gas model. It's a segregated fluid isothermal simulation, meaning the effects of temperature haven't been considered, which affect things like evaporation and buoyancy. If I go into the Lagrangian multi-phase model, you can see that the drag force has been used on the particles, and the turbulent dispersion model, which applies instantaneous fluctuating velocities to the particles to model turbulence. You can also see by the lack of two-way coupling model that I've been using one-way coupling, which should allow the continuous phase to be solved completely independently of the particles. However, there have been some challenges so far, particularly with convergence. This convergence graph is exclusively for the continuous phase, which makes it surprising that there would be a lack of convergence, as it is a very simple inlet-outlet simulation. The main reasons for this are the very low velocities that are simulated, typically around 0.1 meters per second, which most solvers aren't used to handling. Another problem was the effect of the gravity model, which had to be tweaked so as not to cause massive turbulence. Several other solutions were used to improve the results. A solution driver was implemented, different solver parameters were used, and the mesh was changed from a spherical domain with a free stream boundary to simple velocity inlet and pressure outlet conditions. This helped convergence a lot. So here you can see the large turbulence scales that were developing and preventing convergence. So what's left to do before I get on to the main simulations? First of all is to ensure I'm fully familiar with the CFD by validating the numerical results I get, replicating an existing simulation from the literature such as that by Bert Blocken. The second aspect will be to run a mesh sensitivity study to ensure that the mesh is fine enough and stable enough to deal with a range of spray conditions and environmental conditions. The third aspect is to determine test ranges for each of the studies and datum values which will remain constant, Lastly, I have to create some design of experiment studies, particularly for the temperature and humidity simulations, since they are strongly coupled and it reduces the number of simulations needed. Thank you for listening to my presentation on my preparation for the Fluid Mechanics of Social Distancing project. Happy 2021!